Good morning, I'm Mr. Precella with my Math 1325 class. Today we're going to look at the product and quotient rule. This is homework number 4 in my Math 1325 class. The product and quotient rule. I should say product and quotient rules. There are two of them. The product rule and the quotient rule. Remember to find the derivative of a sum or difference. All you do is just differentiate the individual terms. That's easy to differentiate. If you want to differentiate, say f of x plus or minus g of x, all you have to do is just find the derivative of each term. F prime of x plus or minus g prime of x. I guess you could say that that's the sum and difference rule, okay, for finding derivatives. For products, though, you cannot say that the derivative of f of x times g of x, if you have two functions of x being multiplied, you can't say that that's just f prime of x times g prime of x. That is not true. If you're trying to differentiate a product, we have something called the product rule. And I'm going to state the product rule and then we'll look at an example. The product rule. If you want to differentiate f of x times g of x in terms of x, but remember, if I don't put a little subscript right here, then that's whatever letter is appearing in the problem, that's the letter that you're differentiating with respect to. So here's the product rule. It's the derivative of the first factor, f prime of x, times the original second factor, g of x, plus, now you differentiate the second factor, g prime of x, times the original first factor. It's the derivative of the first factor times the original second plus the derivative of the second factor times the original first. And to illustrate that, we'll do number 1. Oh, that pencil isn't dark enough. Here we go. Here's the function that we want to differentiate. And I printed out the homework. That's what I'm looking at right now. This is like your number 1. Y equals 3x plus 5 times 2x minus 3. I think we differentiated this something like this back in the previous homework assignment. Without the product rule, if we can only differentiate sums or differences, we could just FOIL this stuff out and find the derivative. And quite frankly, that's what I would do right now. Okay, if I weren't wanting to illustrate the product rule, I would just FOIL this thing out and then differentiate the terms individually. Why don't we do that? Let's do that. Let's do that right now. Let's just, without using the product rule, here, the thing I'm doing in blue now is without product rule, without product rule. Then we'll redo it using the product rule. Without the product rule, FOILing out, we get a 6x squared outer, negative 9x inner, plus 10x last. Okay. And we can combine the like terms, and that becomes what, a 6x squared plus 1x minus 15. And we know how to differentiate this. So just differentiating the terms individually, we get y prime equals 12x plus 1. The derivative of x is just a positive 1. The derivative of the minus 15 is 0. So we know what the derivative is going to be, and I'll tell you right now, there's never a time I'm going to say I have a binomial times a binomial that I'm differentiating, and I use the product rule. I'll always just FOIL it out and differentiate the terms individually. But to illustrate the product rule in a painless example, that's what I'm going to do right now. So here we go. I'm using the product rule. Using product rule. Let me recopy the problem. Y equals 3x plus 5 times 2x minus 3. If you're differentiating a product, it's the derivative of the first factor times the original second factor plus the derivative of the second factor times the original first factor. We're going to need to know the derivative of 3x plus 5 and 2x minus 3. So let's do that. Let's differentiate. First of all, differentiate 3x plus 5. What does that give us? That's no arrow there. What's the derivative of 3x plus 5? Just 3, okay. Now let's differentiate 2x minus 3. Just a 2. Looking at the statement here of the statement of the product rule, realize that thing there, that's a derivative. This thing right here is the derivative. So here we go. We're differentiating. I'll use this color. Y prime equals, it's the derivative of the first, this 3 here, times the original second. It's the derivative of the first times the original second factor, that red 2x minus 3, plus the derivative of the second, 2, times the original first, 3x plus 5. The derivative of the first factor times the original second plus the derivative of the second factor times the original first. And now we can clean this up by distributing through the 3. That'll give me a 6x minus 9 plus here 6x plus 10. Combine our like terms. That's going to give me 6x plus 6x. There's the 12x. Negative 9 plus 10 gives me a 12x plus 1. Is that what we got up there when we were differentiating? Yeah. In both cases, we got a 12x plus 1. The derivative of the first times the second, the original second, plus the derivative of the second times the original first. I want to do one more product rule before we look at the quotient rule. Okay, this is number 2. And you don't have to be worried that if you say the wrong answer, this recorder, the mic doesn't pick up what y'all say anyway. So you can say anything, and even if it's wrong, and I'll just go on pretending that it's right, okay? So, yes, the recorder doesn't pick up what y'all say. Oh, and if you look at the homework, it doesn't tell you to use the product rule. It just says, number 1 said use the product rule. Number 2 just says differentiate. but it's a product, so I'm going to use the product rule. We have two separate factors. We have 7x to the fourth minus x plus 5. That's the first factor. It's enclosed in parentheses. The second factor is that negative x to the fifth plus 2. We need to differentiate each factor. So let's differentiate 7x to the fourth minus x plus 5. What's that going to give us? 28x cubed. Keep going. Minus 1. What about the derivative of negative x to the fifth plus 2? Okay, so there's a little arrow. Negative 5x to the fourth. Anything else? No, because the derivative of 2 is 0. You know, I'm just so used to writing without lines that even when I'm using lined paper, I just ignore the lines. I should be trying to keep everything on lines because that's how y'all write it. But here we go, using the product rule. It's the derivative of the first, the 28x cubed minus 1 times what? The negative x to the fifth plus 2. The negative x to the fifth plus 2 plus, okay, the derivative of the second, negative 5x to the fourth times that trinomial 7x to the fourth minus x plus 5. Notice the way I write the derivatives underneath, there's almost a crisscross pattern. The derivative of the first times the second plus the derivative of the second times the first. And I'm betting anything if my math lab would say that you have to simplify this. I don't think they'd accept this as a final answer. So let's go through and simplify now. We have y prime equals, foiling this out, 28x cubed times a negative x to the fifth. That's going to give us a negative 28. How many x's are we going to have? 8. Add in the 3 and 5, that's an 8. Outer, that's a plus 56x cubed. Inner, that'll become a positive 1x to the fifth. Last, minus 2, okay. So we FOILed out the first two sets of parentheses, binomial times a binomial. What are we going to have to do here? Distribute the negative 5x to the fourth, there, there, and there. So that's going to become a negative 35x to the 8th, I agree. Negative 5x to the fourth times a negative x, that's going to give me, I'm running out of room, I'll have to come over here. A positive 5x to the, I can't hear you, 5th, I agree. 4 plus 1, so we had 5 factors of x. This last product, negative 25x to the fourth. And now let's combine all of our like terms. That doesn't look like a 5. Can y'all tell that's a 5 there? I think I'm just making it worse, aren't I? So y prime equals, I think I'll start off with the biggest exponent. The biggest exponent is what? X to the 8th. So we have a negative 28x to the 8th minus a 35x to the 8th. That gives us a, okay, so a negative 63x to the 8th. I just took care of the x to the 8th. And then the next exponent is what? X to the 5th. Okay, so 1x to the 5th plus 5x to the 5th, I agree, that's a plus 6x to the 5th. And then we have our x to the 4th, there's only one of those. We have an x cubed, a plus 56x cubed, and a minus 2. Once again, I guess we could have gotten around using the product rule by distributing that trinomial over negative x to the fifth plus 2. You say, well, that's a lot of multiplication, but it would have saved you all of this here, so it's just a matter of trade-offs. You could have gotten around this pretty painlessly without using the product rule, but I wanted to illustrate the product rule. Any questions there? Now the quotient rule. Let's see, the quotient rule. If you want to differentiate with respect to x a quotient, f of x divided by g of x. It's equal to, it's the derivative of the numerator, f prime at x, times the original denominator, g of x, minus the derivative of the denominator, g prime of x, times the original numerator, f of x. The denominator, you take the original denominator and square it. So whatever that denominator is, g of x, you square it to get the new denominator. It's the derivative of the top times the bottom minus the derivative of the bottom times the top. I'm going to use the terminology I used with the product rule. Remember, with the product rule I would say the first and the second. So it's the derivative of the first times the second, but instead of a plus in the product rule we have a minus the derivative of the second times the first. So the numerator looks an awful lot like the product rule, with the exception of that minus there. And note, to differentiate a fraction, you can't just differentiate the numerator and differentiate the denominator. I'll say note. If you're differentiating f of x divided by g of x, that does not equal f prime divided by g prime. And the for multiple choice problems, I don't know if there's any multiple choice problems in the homework, but if there are, they'll invariably, one of the distractors for a messy rational function, they'll just differentiate the numerator and differentiate the denominator. So, and that's certainly not correct. Let's use the quotient rule now, and I have a problem right here I want to do. This is like y'all's number 4. This is like your number 4. Here goes. I want that quotient rule sitting right there. They want us to differentiate y equals 6x minus 1 all over 8x plus 9. And realize we have variables in the numerator and the denominator. We have a function of x divided by a function of x. Now, we were differentiating some problems where the denominator was just a number. If the denominator is just a number, I wouldn't use the quotient rule. I would then do the little trick of writing it as a fraction the way we were doing in the other homework assignments. But if that denominator contains a variable, in this case there are 2 terms, 8x plus 9, then I would certainly use the quotient rule. We need to know the derivative, so let's differentiate. What's the derivative of 6x minus 1? 6. What's the derivative of 8x plus 9? 8. So here we go. Y prime is equal to, and it's going to be a fraction, so I'm going to write the fraction bar. It's the derivative of the first times the original second. So the derivative of the first is 6 times the original second, which is an 8x plus 9, minus the derivative of the second, 8, times the original first, 6x minus 1. The denominator, you just take the original denominator and square it. The original denominator is 8x plus 9, and you square it. The derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. When I'm using the quotient rule, I'll draw my little arrow out beside it and I'll differentiate the numerator. I'll draw my little arrow out beside it, I'll differentiate the denominator because I need those, but the derivative is not 6/8. The derivative isn't 6/8. But you need to know the derivative of the numerator and the derivative of the denominator to use the quotient rule. In most cases, I'll tell you right now, you won't want to expand that denominator when you use the quotient rule. It's already in factored form, 8x plus 9 quantity squared. You're not going to want to go through FOILing that out, okay? In most cases, the vast majority of times, you just leave the denominator the way it is. Sometimes there's some reduction that you have to do, but most of the times, that's not the case. We can distribute the 6 over the 8x plus 9. Distributing the 6 over the 8x plus 9, we get a 48x. What else? Plus 54. Distributing the negative 8 over the 6x minus 1, we get a minus 48x and a plus 8. This is actually working out pretty nicely. We have an 8x plus 9 quantity squared in the denominator, and on top we have a 48x minus 48x. The x's are gone. We have a 54 plus 8. Gives me a numerator of 62. For our final answer of 62 over 8x plus 9 quantity squared. One thing that you'll notice after using the quotient rule for a while, there's not a lot of simplification. People will incorrectly want to cancel in this initial step right here. They'll see 8x plus 9 above and below and they'll decide to cancel. You can't do that. 8x plus 9 is not a factor. This numerator is not in factored form. So you can't start canceling. If you could cancel the 8x plus 9 right here, now see where I'm pointing? Right there. If you could cancel there, then why don't we just cancel a g of x in the original statement of the quotient rule? If we could cancel the 8x plus 9 there, we can cancel a g of x. So that we don't have that g of x squared in the denominator. We don't have that g of x up there. If you're using the quotient rule and you're doing a lot of cancellation, you're doing something wrong. It is that simple. There will be some problems where we'll be able to go through and deliberately take the result of the numerator and factor it, so that we can pick up a common factor to the denominator and cancel. But that is a very rare event, and it's not something that happens accidentally, okay? It happens further down in the problem. For the most part, if you're using the simplex method and you're doing a lot of not simplex, if you're using the quotient rule and you're doing a lot of canceling, you're just doing something wrong. Any questions there? Okay. Number 5. I want to save these because before we're through today, I'll go and log on to my math lab and we'll punch in. We'll do number 5 right here. Here's number 5. Okay, so right there. Okay, here's the function they want us to differentiate. 8x squared minus 7 divided by 5x cubed plus 1. And once again, I just printed out the homework. And you'll notice it doesn't say use the quotient rule. I don't have to tell you that because you have no other way of doing it. I guess once we see the chain rule, you could rewrite that denominator using, for 4 and 5, you could rewrite it using negative exponents. But that'd be even messier than the chain rule. So even without saying use the quotient rule, you have no other way of doing it other than the quotient rule. It's a function of x divided by a function of x. So with that in mind, we need to know the derivative of the numerator and the derivative of the denominator. Let's see, I think I'll use, does orange show or is this an invisible ink? Does orange show? It doesn't show that well. How about this color? Let's differentiate the numerator. The derivative of 8x squared minus 7 is just 16x. The derivative of 5x cubed plus 1, what's that derivative? 15x squared, I agree. And now we're going to use the, I think I'll go back to red. Now we're going to use the quotient rule. Using the quotient rule, we get y prime equals it's the derivative of the first, that's 16x times what? Okay, 5x cubed plus 1. It's the derivative of the first times the original second, sine minus the derivative of the second, 15x squared, times what? Okay, the 8x squared minus 7, the original first. You all see that crisscross pattern. Derivative of the first times the second minus the derivative of the second times the first. That's the same way I say the product rule, except instead of a minus, they have a plus there. You have the added fact, since this is the quotient rule, you have the added denominator, that 5x squared plus 1, no, 5x cubed plus 1, we have to square it. Hey, we have two 5x cubes plus 1 down here and 1 up there. Maybe we could cancel? No, we cannot. That numerator is not in factored form. So here we go. Let's start removing the parentheses, distributing the 16x over the 5x cubed plus 1 we get an 80x, how many x's? 4 plus 16x, I agree. And here, distribute the negative 15x squared there and there. We're going to get a negative 120. How many x's? X to the 4th and a plus. Is that a 105? X squared. And we still have that 6x, no, that 5x cubed plus 1. Quantity squared in the denominator. And I'm assuming those of you sitting out there in the audience, if I move this paper and it stops showing what I'm writing, you'll tell me, right? Yes? Okay. So 5x cubed plus 1, quantity squared. Combining the, let's start off with the x to the 4th terms. That's the biggest exponents. Negative 40x to the 4th. And I just took care of these two. And we have 105x squared and and the plus 16x. And that numerator may be factorable. I know one thing we could do to the numerator. We could factor out a common factor of x. But here's how I decide. When I have something like that left over in the numerator, I ask myself, if I were to factor that, would I pick up what I have down in the denominator so I could cancel out a factor? 5x cubed plus 1. As I play out, factoring out that 1, x to the first power, and then start trying to factor the thing that's remaining, I don't think I'd get a 5x cubed plus 1 to cancel in the denominator. And since I don't think I'm going to get another one of those, I'm not going to waste my time trying to factor the numerator. I'm going to stop right here. As I said, the only way you can wind up doing some sort of cancellation is if you deliberately go through. Now I'm going to factor the numerator, and in the factoring process, you pick up a common factor in the denominator. And eventually that will happen. That will happen, but it's not something that happens accidentally. It's something we deliberately set out to do. Any questions there? And I have one more I want to do today. This is number 6. Let me move my paper down. This is number 6. And y equals x squared minus 2x plus 5 all over x plus 8. And this is number 6 right here. And you'll notice on number 6 they do specifically say use the quotient rule, but even if they didn't, there's no other method you have at this point that would be sufficient. Once we see the chain rule and the general power rule, you could rewrite it using negative exponents, but certainly wouldn't be easier than the chain rule. So, it certainly wouldn't be easier than the quotient rule. So, we're taking the easiest approach there is at this point. If we're going to use the quotient rule, we need to know the derivative of the numerator and the derivative of the denominator. So let's differentiate the numerator. (2x minus 2), okay. What's the derivative of x plus 8? We need the derivative of the denominator. 1. So, using the quotient rule, we have y prime equals, it's the derivative of the numerator, 2x minus 2, the derivative of the first times x plus 8, it's the derivative of the first times the second, sine minus the derivative of the second, 1, times x squared minus 2x plus 5 all over x plus 8 squared. I never really thought about the crisscross pattern I use until I would do the same setup when I was teaching a regular calculus class. And I remember one day, this was several years back, it was over 10 years ago, I remember it like it was last week, a colleague of mine who always came into our office for coffee, back when we would drink coffee in there, and he said, and he was teaching calculus too, and he said that, what is this crisscross rule that you use? Your Cal 1 students, they all went into Dr. Hoyt's Cal 2 class, and he said they call the quotient rule the crisscross rule. I said, I have no idea. We use the quotient rule. And I went on and didn't think anything about it. And then I was teaching the course, going through, and it dawned on me what they were calling. He said the crisscross rule was the same as the quotient rule. They got the same derivatives, but they weren't calling it the quotient rule. This is the quotient rule, okay? It looks, if you're setting it up the way I'm doing it, you see a crisscross pattern. Derivative of the first times the second minus the derivative of the second times the first. This is the quotient rule. And so, but those students of mine were using the crisscross rule. They even used it for products. They used the same rule for products and quotients, and they'd get the correct derivatives, but Dr. Hoyt said he never seen this crisscross rule. Oh, what you students come up with. Okay, so there's my denominator, x plus 8 quantity squared. Let's FOIL out the numerator. Let's remove the parentheses first. Two x squared outer plus 16x inner minus 2x last minus 16, and distributing through that negative 1 there. The only reason I even put the 1 there is so that it's obvious. You got to distribute that negative through. If I didn't put it there, some people might want to only stick the negative on the x squared and not change the other signs. It'll become a minus x squared plus 2x into minus 5. And 2x squared minus 1x squared, that's giving us 1x squared. 16x minus 2x gives us a 14x, plus another 2x, so that's giving us back the 16x. Oh, what all have we done? We've taken care of this and that. What have we got? No, that. We haven't done the negative 5. Negative 16 minus 5, that's going to give me a minus 21 all over x plus 8 quantity squared. Even if we tried to factor the numerator, it turns out the numerator isn't factorable, but if we tried to factor it and it were factorable, we wouldn't pick up another x plus 8. The only way I would try to factor this is if I were reasonably confident that I'm going to factor it and pick up an x plus 8, in which case I can cancel one of those x plus 8s in the denominator. That is the only way that I would factor in the start factoring the numerator, is if I'm reasonably confident that I'll be able to pick up one of these factors from the denominator and cancel. Even if this were factorable, then I wouldn't factor it unless, suppose that were an x squared plus 4x minus 21. That's factorable, but it doesn't give you an x plus 8, so why bother? You're not going to be able to cancel a common factor.
So if it was x squared plus 16x plus 64, then you'd be able to factor it?
You'd be able to factor it as an x, but in that event, you'd factor it as a x plus 8. It all reduced to 1, though. I think you'd pick up an x plus 8 times an x plus 8 that you could cancel and just give you a derivative of 1, which certainly isn't going to happen. But if there were something that you could pick up an x plus 8 off when you were factoring, I'd factor and cancel. And any questions there? Let's stop a moment so I can punch in the answers and make sure that all of our work's correct. So I'm going to take a break from writing now so I can punch in my answers on my math lab. Bye-bye.